The first challenge is when a model is executed in a static graph mode, but not in dynamic graph mode. The procedure of executing a model by means of the static graph mode is to define the model first. Next, we feed the data to the model by the data loader. The model executes along the flow of the nodes and edges. However, user is out of control. The forward path continues until completion. Once forward propagation completes, then backward propagation starts. The model parameters update. In comparison, the dynamic graph execution mode is different from the static graph mode significantly. User defines the model first, but the execution proceeds step by step for each layer in a debug-friendly way. The computation graph executes in a way faithful to the code written by the user, and by running each mode, the intermediate result is returned to the user immediately. So, static graph mode is more challenging to control. Dynamic graph mode relieves the development and implementation of preemption, graph suspension and resumption, parameter transfer. The second challenge is that framework is agnostic to nodes from different users. Also, TensorFlow framework is lack of an effective and efficient preemption mechanism to suspend, resume running jobs, not to say enforce priority. The framework and GPU are incapable of making a distinction between different users. FIFO is a default scheduling in the framework runtime. When a training job is submitted by user A and the user B also submit inference job, although GPU supports multiple jobs, job B will be severely delayed. Since inference jobs have stringent SLOs, it is not desirable. Even worse, packing too many jobs on a GPU will incur out-of-memory problems. As we know, each job can be abstracted as graph computation. When we run two jobs in the diagram, nodes from different graphs are sent to GPU simultaneously. Nodes are not differentiated in execution order from different users. Also, nodes execution cannot be interrupted from users, framework, and GPU side. We propose SwitchFlow to solve the above-mentioned challenges for multiple users sharing a pool of devices, including GPUs and CPU. The main part of the system is session management. It enforces priority of different users. Within each session, it consists of multiple executors to execute subgraphs partitioned across different devices. Subgraphs are replicated for both CPUs and GPUs. For example, data pipeline subgraphs are placed on CPU convolutional operations. Those are placed on GPUs. The underlying dispatching is achieved by eigen libraries, thread pool, and multi-queue. Nodes are aggregated as tasks that are dispatched to multiple queues. In addition to the global thread pool queues, we design a temporary queue for preempted jobs, which dispatches nodes to other devices. In this case, we can separate different nodes from different computation graphs. Threads in the thread pool can steer tasks between different queues to keep workloads balanced between different queues. Finally, nodes are executed by invoking CUDA runtime or CUDIN libraries asynchronously on GPU. Preemption is enforced by suspending all outstanding operation nodes in the global queue. The dispatched kernels to GPU is unable to be suspended. Based on those two kinds of queues, we can make sure that preempted jobs is not suspended at all, but are moved to another queue. The OP nodes in that queue are dispatched to the devices with low computational capability. Also, we need to handle weights or model parameters between devices after we migrate jobs to another device. The preempted jobs model parameters are migrated from one device to another. Since the session is not distracted, so do parameters, and all devices are shared by the session manager. We only migrate model parameters but not all intermediate data. In the meanwhile, session manager constructs new executors for the high priority job to be executed on GPUs. Another design is to improve GPU utilization by reusing input data for similar models. As computation graph spans across CPU and GPU, reuse data from the subgraph opens up new opportunities to speed up consecutive jobs. The idea is to enforce the order of model to access the data from CPU side. We also consider different models with same data preprocessing. In this work, we have implemented a prototype of SwitchFlow in TensorFlow. We made changes to TensorFlow with 3,000 lines of Python and C++ code. Most changes were made to TensorFlow session and executor, as well as the provision of the temporary thread pool and preemption. Models are launched from the same TensorFlow instance via multiple Python threads. Environment variables are set to share data loader. Experiments were conducted on two servers and adjacent TX2 development kit. One server was equipped with two different Nvidia GPUs, GeForce GTX 1080 Ti and RTX 2080 Ti and another server with 4 Nvidia Tesla V100 GPUs. We implement SwitchFlow on TensorFlow and use the variants of TensorFlow with the same version for comparison. Benchmarks are multiple CNN models that selected from the Keras applications like Resonant 50 VG16 and one recurrent neural network, NMT. We evaluate the effectiveness of preemption and data reuse by showing performance in tail latency, throughput, and preemption overhead. The baseline is Nvidia MPS Vanilla TensorFlow, multi-threading execution, and session-based execution. To evaluate the effectiveness of SwitchFlow's preemption mechanism, we co-run an inference job with a background compute-intensive training job. Inference requests were configured with higher priority and each contained only one image. We first launched the background training job. The baseline was the multi-threaded TensorFlow running training and inference in separated threads. This figure shows a 95th percentile tail latency of inference when co-run with the background jobs. The background training job is Resonant 50. The conclusion is that without preemption mechanism, all jobs with high priority are severely delayed. This slide shows the throughput performance of SwitchFlow. The bars in each group correspond to the performance of the two models, with arrow showing the performance degradation compared to that running in solo. Multi-threaded TensorFlow causes OM errors when the aggregated real-time memory demand of the two models at any point exceeds device memory. Even worse, all models crash under Nvidia MPS on the 1080 Ti and 2080 Ti GPUs because the two processes in MPS, each running a separate model, do not share GPU memory allocation. Thus, when the aggregated peak memory demand exceeds GPU capability, training will crash. For SwitchFlow in the figure, upon the arrival of a high-priority model, the low-priority one is preempted and migrated to a different device. Whether it be another slower GPU or CPU, we make the following observations. There was no crash. In all cases, a high-priority job achieved a much higher throughput than that in multi-threaded TensorFlow. The lower priority job achieved acceptable throughput when migrated to a slower GPU. Preemption overhead in SwitchFlow involves aborting the exception of outstanding model nodes. Preemption overhead in SwitchFlow involves aborting the execution of outstanding nodes, allocating space on a destination device, transferring model states to the destination, and freeing the memory of the model states on the source device. This table shows overhead of model state transfer. For example, the state for variable of Resonant 50 is 198 megabytes, and the transfer time between GPU to GPU is 28.8 milliseconds. In this slide, the figure shows significant improvement when two identical inference jobs were collocated. Input reuse saved as much as 65% compared to session-based time slicing. This figure shows the performance improvement due to interleaving executors of independent model against the session-based time slicing. When co-run with training, the gain diminished for lightweight models, for example, MobileNet V2, and the gain was up to 20%. In summary, SwitchFlow enables preemptive multitasking for deep learning with fast preemption and high utilization. SwitchFlow maintains multiple versions of each subgraph. SwitchFlow schedules its subgraphs and prevents subgraphs from different models to run simultaneously on a GPU. Subgraphs running on different devices can overlap with each other, leading to a more efficient execution pipeline.